Hello, welcome to another module in this massive open online course. So, let us start our discussion on optimization by looking at some of the fundamental building blocks of optimization by first looking at convex sets, the notion of a convex set and the various properties of convex sets. Okay. So, we want to start our discussion of optimization, and one of the important concepts to understand in convex optimization is a convex set, the definition and properties of convex sets. Okay. So, a convex set is as follows. Now, consider, so define a convex set, let us start with the following setup. Consider 2 points x1 bar comma x2 bar in n dimensional space, okay, which means these are vectors in n dimensional space. These are points in these are general points in n dimensional space. Okay. So, we are considering 2 points in n dimensional space. Let me describe these points. So, I have point 1, let us say this is your x bar and this is your x bar, and this is the line segment, that is joining x line segment between x1 bar and x2 bar. Okay. This is the line segment between x1 bar and x2 bar. Now, consider now a linear combination of the form theta x1 bar plus 1 minus theta x2 bar 1 minus theta x2 bar such that, well, 0 is less than or equal to theta is less than or equal to 1. Okay. So, we are considering a combination of x1 bar and x2 bar such that with the weights theta and 1 minus theta, that is theta times x1 bar plus 1 minus theta times x2 bar. And another important aspect to note here is that we are not allowing any value of theta, but only values of theta lying between 0 and 1. Okay. And now, for instance, let us take a look at the various such points generated by this combination. Now, for instance, if theta equals 1, let us denote this point by x bar. We have x bar equals, well, 1 times x bar plus 0 times x 1 times x1 bar plus 0 times x2 bar. So, this is x1 bar. If theta equals 0, on the other hand, x bar is simply, you can check, theta equals 0 times x1 bar plus 1 times x2 bar. So, this is x2 bar. If theta equals half, this is half times x1 bar plus half times x2 bar. So, this is x1 bar plus x2 bar by 2 equals x bar, which is basically, you can see, midpoint of the line segment between x1 bar and x2 bar. So, this you can see is the midpoint of the line segment between x1 bar and x2 bar. So, what you observe is that as theta varies from 0 to 1, this combination theta times x1 bar plus 1 minus theta times x2 bar traces the line segment between x1 bar and x2 bar, correct. So, theta times x1 bar plus 1 minus theta times x2 bar traces line segment between x1 bar comma x2 bar for various values of 0 less than equal to theta less than equal to 1. That is theta times x1 bar plus 1 minus theta times x2 bar. If you look at this combination, which is also termed as a convex combination, this denotes a point on line segment between x1 bar comma x2 bar for any particular value of theta lying between 0 and 1. Okay. So, as theta varies from 0 to 1, it traces the line segment between x1 bar and x2 bar. Okay. That is the first basic concept. Okay. Now, what is the definition of a convex set? A set is known as a convex set. A set is termed as a convex set if for, that is, if any two points x1 bar comma x2 bar belong to S, then the entire line segment not the line, the entire line segment between x1 bar and x2 bar comma x2 bar belongs to S. Okay, this symbol is basically belongs to. Alright. So, what this means is the following: if mathematically writing, if x1 bar comma x2 bar belongs to S, implies that the line segment, remember we just demonstrated that the line segment is denoted by x1 bar theta times x1 bar plus 1 minus theta times x2 bar, 0 less than or equal to theta less than or equal to 1, also belongs to S for all, that is for any x1 bar, for all, that is for all 0 less than or equal to theta less than or equal to 1. So, what this says is, that is, if you pick any 2 points x1 bar x2 bar belonging to the set S, then if the entire line segment between x1 bar and x2 bar belongs to S, and this is true for any such set of points x1 bar x2 bar, such a set is known as a convex set. And the mathematical way of stating this is that if you pick any 2 points x1 bar x2 bar, construct theta times x1 bar plus 1 minus theta times x2 bar, which represents a point on the line segment for various values of theta between 0 and 1. This point represented by theta times x1 bar plus 1 minus theta times x2 bar must belong to X, must belong to the set S. Okay. It is a very simple example, it is a very simple definition. For instance, you can readily see that an ellipse is a convex set. This can be formally also shown, which we will show later. That is, you can choose any 2 points and the entire line segment joining the 2 points you can check lies in the set. So, for any 2 points, entire line segment is contained in set. So, for any 2 points in set, entire line segment is contained for any 2 points in the set, the entire line segment between them is contained in the set. For instance, you can also quickly check many other sets such as hexagon for instance, and these need not be regular shapes. For instance, a hexagon, you take any 2 points, you join them by the line segment. So, the hexagon you can clearly see is a hexagon is also a convex set. Okay. On the other hand, if you have a region like this, you can clearly see this kind of a set is not convex because if you take any 2 points and join it by a line segment, then the line segment is not entirely contained in S. The line segment, you can quickly verify, the line segment, part of the line segment lies outside this set S. So, if this is your set S, S is not convex. Okay. So, you take 2 points and join them, part of the line segment lies outside the set S, that is, the line segment is not entirely contained. Remember, it is not just a few points of the line segment, the entire line segment has to be contained in S, only then, and that has to be true for any set of points in S. Now, for instance, you can look at this, even though if you choose these 2 points here, then the line segment is contained in S, right, but it is not only for a particular set of points, this has to be true for any set of points and the entire line segment between that chosen set of points, alright, that has to be completely contained in S. Okay. Let us come to the notion of a convex combination. Another very useful notion is that of a convex combination. And a convex combination is as follows, that is, if I have, remember we said theta times x1 bar plus 1 minus theta times x2 bar, consider this combination, I can equivalently represent this as theta 1 times x1 bar plus theta 2 times x2 bar, but they have to satisfy the property, remember theta 1 plus, because remember we have theta and 1 minus theta. So, that implies theta 1 plus theta 2 equals 1 and 0 less than, theta lies between 0 and 1, which means we have to have the property 0 less than or equal to theta 1 comma theta 2 less than or equal to 1, or you can equivalently say that theta 1 comma theta 2 or theta 2 comma theta 1 greater than or equal to 0 and theta 1 plus theta 2 equals 1. Okay. So, a convex, such a combination is known as a convex combination. This is known as a, termed as a convex combination of x1 bar and x2 bar. Now, I can generalize this notion of convex combination. Now, what I can do is I can generalize, starting from here I can generalize this notion of convex combination to include n points. So, you consider k points k points in n dimensional space, that is x1 bar, x2 bar, so on up to xk bar, and you consider theta 1, theta 2, theta k, such that theta 1 plus theta 2 plus theta k equals 1, and each theta I is greater than or equal to 0, and perform the combination theta 1 x1 bar plus theta 2 x2 bar plus so on theta k xk bar. This is termed as a convex combination of x1 bar, x2 bar and up to xk bar. So, this is a convex combination. This is a convex combination of x1 bar, x2 bar up to xk bar. So, let us now look at the convex hull of a set. So, the other concept we want to look at is the notion of a convex hull, and the convex hull of a set is simply, it is nothing but basically this is the set of, so given set S for convex, the convex hull is the set of all of convex combinations, set of all convex combinations, set of all the convex combinations. All the convex combinations of points in S. So, you take a set, okay, for any given set, consider the set of all the convex combinations of the points in S, and that gives the convex hull of the set. Now, naturally observe that for any convex set S, the convex hull is the set itself, because S, if S is a convex set, then it already contains all the convex combinations of the points in S. Okay. So, for a convex set, for instance, we saw yesterday that the hexagon is a convex set, correct. For a convex set, convex hull equals the set itself, okay, because it already contains all the combinations, convex combinations. For a non-convex set such as this kind of region that we look, this is a non-convex set. For a non-convex set, the convex hull simply fills this region to make it a convex set. So, the earlier one is a non-convex set. So, now once you fill this, what you get, that is this entire set that you get is now a convex hull. So, the convex hull that makes it basically, that converts it, you see, you can say includes all the convex combinations of all the original points in the set S to convert it into a convex set. That is the convex hull of a given set S. Alright, so let us stop this module here and we will look at other aspects in the subsequent modules. Thank you very much.